Yesterday, we spent time reviewing real quick how to find the area under a curve, or the area between a curve and the x-axis, and how we had to consider area above our x-axis, area below our x-axis, and I would just want to point out that everything that you did on the worksheet was all one function. Today we're going to look at area, but area between two functions, or between two curves, is our focus. And we'll talk about how there is overlap between these, and it's not super obvious, but there really is an overlap between what is going on. So as we look at the area under two curves, that formula down there says if f and g are continuous functions and f is greater than g on an interval from a to b, the area that falls between them is from a to b is the integral of f minus g. So I want to look at what is going on here. We've got some function f of x in our picture. And we've got some function g, and the area under that curve would be all of this, right? And what is represented by what I just highlighted there would be the integral from, let's say, if we call this a to b, of that function f of x. Agreed? And if we were to put a second picture in there, let's say some function g of x, that the area under that curve would be represented by the integral from a to b of g of x. Good? But if I wanted the area that was between the curves, so the area between the curves would be like here. Like the blue stuff, wouldn't I just be subtracting the red out of the black? Right? That's what it is. And so it would be subtracting what I got for those two integrals, or showing this, the first one, minus the second one. Well, if they're just two functions, and it's addition or subtraction, can't I just subtract the functions? And that's where that's coming from, is that we can just take the top function minus the bottom function and find the integral of the result. Yep. Nope. Nope, we can't integrate separately for multiplication. Yep. Okay, so that's where that function, or that formula is coming from for the area between two curves, is that it's your top function minus your bottom function, and important that you put it in that order. Top function minus the bottom function as we do that. Okay, and give you a little hint for later in your assignment, if that were to ever flip, we would have to break that up into two different intervals, because it always has to be top minus bottom. Okay. All right, so looking at an example of that, our first two examples we're going to do today are going to be non-calculator. And this one's pretty straightforward as far as how to do non-calculator. The directions in the top say find the area, which is our shaded blue region there, between the functions y equals secant squared of x and y equals sine of x from 0 to pi over 4. So they are coming out in the directions and telling us our interval of integration, and that would be from 0 to 4. So what we just learned on the last page says that the area between those curves is found from taking the top function minus the bottom function and integrating from 0 to 4. So our top function would be secant squared x minus our bottom function, which would be sine of x. And as always, including our variable of integration. That variable of integration is going to become incredibly important to us over the next week or so. So making sure that we are always including that. And I did tell you that this was a non-calculator. Those really, we absolutely can find the antiderivative of each of those. And again, it's got a subtraction between them, so we can do them separately, right? The antiderivative of secant squared, tangent. And, ooh, careful on this one. Antiderivative of the minus sine x, cosine of x, right? Plus cosine of x, yes? Okay. And we're going to integrate from 0 to pi over 4. So this is where we got to remember a little bit of unit circle stuff here. So evaluate it at pi over 4. Evaluate at 0. All right, let's see if we remember our unit circle. What is the tangent of pi over 4? 1. Cosine of pi over 4. There we go. All right. Minus, and I can distribute that negative through tangent of 0. 0. Cosine of 0. Right. Cleaning that up, I have 1 plus square root of 2 over 2 minus 0 minus 1. 1 minus 1 is gone. So we'd be left with square root of 2 over 2. Top minus bottom, integrate on the interval given. Questions? All right. What if our curves intersect? A lot of times then they'll ask us for the area between those curves, but not tell us the interval on which we are supposed to look. So when a region is enclosed by the intersecting curves, the intersection point gives us the limits of integration. So our example of this, and again, I'm going to stick with non-calculator here for one more example. Find the area of the region enclosed by the parabola y equals 2 minus x squared and the line y equals negative x. One of the things I would always encourage you to do is just draw a picture of what's going on so you can visualize, especially as we have to think through what is our top function and what is our bottom function. Since we're finding the area between them, we need to subtract top minus bottom. So as we draw this one, I've got that first function, y equals 2 minus x squared. They said it's a parabola. Because of the minus x squared, we know it's an upside down parabola, right? Moved up 2. Agreed? Remember in all of our transformations here? So it's going to look something like that-ish, right? And I've got a function that is the line y equals negative x. That's in our y equals mx plus b. So it's going to go through at my origin, slope of negative 1. Ooh, I missed there. Okay. And we are supposed to find the region enclosed by that, which would be all of this area here that is between those two curves. So we would set up our integral. Top function was that parabola, 2 minus x squared minus our bottom function, which was negative x. The problem is they didn't directly tell us from where to where we are finding that area. And so it becomes where those two functions intersect each other. So I need to find these points of intersection. Now remember, especially when we don't have a calculator to find that for us, to find points of intersection, we find where those two functions are equal to each other, right? So to find our points of intersection, set the two equations equal to each other. Our two equations being negative x and 2 minus x squared. This is where we got to remember our algebra. We've got x's, x squareds, plain numbers. That means get everything onto the same side and either factor or quadratic formula, right? So I'm going to move everything to the left-hand side here. Factors of negative 2 that add up to negative 1, do they exist? Negative 2 and 1, right? Which means, now, typically I would go find the end of that ordered pair, right? I got x values for each of those ordered pairs. This is -1 comma something. This is 2 comma something. It's really easy to figure out because I can just plug them back into this equation right here. However, all we need to know is from where on our x-axis to where on our x-axis are we integrating or finding that area. So I really only need the x values of those points of intersection because we are integrating with respect to x. Okay, so it would go from -1 to 2. Questions so far? All right, let's go ahead and evaluate this integral. I'm going to rewrite mine in standard form just because it cleans it up a little bit. Power rule on that, each of those terms. I've got -1/3 x cubed plus 1/2 x squared plus 2x evaluated from -1 to 2. Plug in 2, plug in -1. This is where we make a lot of our mistakes, so make sure that you are kind of always double checking your work at this point. 2 cubed is 8 times -1/3 would be -8/3. Oops, I forgot a squared there. 4 times 1/2 is 2 plus 4. -1 cubed is -1 times 1/3 is 1/3. That'd be 1 plus 1/2. That'd be -2. Distribute our negative through here. Just kind of making this a little bit easier. -8/3 minus 1/3 would be -9/3, and -9/3 is -3, right? So I can put my thirds together and to get -3 plus 2 plus 4 minus 1/2 plus 2, right? So that would be what? 6, 8, minus 3 is 5, negative, so 4.5. Yeah. Okay, any questions so far? All right. We are going to then transition into what becomes calculator problems. It says find the area of the region enclosed by the graphs of y equals 2 cosine x and y equals x squared minus 1. Go ahead and get that copied into your notes, and then we'll look at how to kind of start this one. First things first, get a graph. So I typed those two into my y1, y2. You can guess and check a window for that. Probably could have zoomed in a little bit more, but I get the picture. I see what is going on. Okay. One of the things that we will want to do for ourselves is just draw a picture. So we've got our parabola here. And we've got our sine function here. Something like that. And the area between our two curves. Then or cosine function, whatever it was, would be that shaded region. So that's what we're going to answer at the end of this, the area between those two curves. We don't know our points of intersection, and these are not easy ones to just set equal to each other. That's why we're going to rely on our calculators. So I'm going to go find this point of intersection using my calculator functions, which should be second 5 intersect here. Go close to that point of intersection, hit enter, enter, enter. And it does tell you an ordered pair. So remember what we want from that ordered pair. They are telling us the ordered pair is -1.265, comma 0.601. And our other point of intersection. Okay. But we're writing these in terms of x. We're integrating with respect to x, which means we want our x values on this. So those would be my integral intervals from -1.265 up to 1.265. Top function, you got to remember which one is which in this. Your top function is going to be your cosine, right? 2 cosine x is our blue graph here. And then this is where we got to be careful here. Minus, and if your second function, especially if it's a polynomial or more than one term, you have to subtract the whole thing. I would put it in parentheses, or you can distribute. It doesn't matter. But make sure you are subtracting the whole thing. If I just put minus x squared minus 1, without parentheses, it becomes a different function, right? Because now that negative was distributed through something else. So make sure you get that parentheses in there. And then we're just going to grab our calculators and integrate. Math 9 that for me. .995. Questions? Okay. We can't just be robots, so we have to make sure that we are always paying attention to what is going on. And sometimes it takes some analyzing, sometimes it takes some manipulating of the picture we've been given. We've now been looking at one function and how we can break that up. We've looked at 2 functions. And so what happens if we've got something else, like 3 functions? Okay. So I'm going to give you a second here to get that picture into your notes so you can write all over it, and it asks us to find the area of the enclosed region. The problem is in that we have in here 3 functions. Our method only worked for 2 functions, and it talked about if we were finding the area between 2 functions, not 3. So we need to manipulate what's going on here a little bit so that we can still find that area using the tools that we have. Okay. The problem is, as we move across this picture, when we talk about the top function minus the bottom function, doesn't that kind of shift in our shaded area As I go across my shaded area here, what is the top function right now? Y equals x, right? Of my shaded region, this would be my top of the shaded region, right? And that would be y equals x. Agreed? Okay. Just what's shaded. All we're doing is finding the shaded region. Okay, so shaded region, top function is y equals x. When I get to this point, again, of my shaded region, my top function is now y equals 1. So at this point, our top function changed, didn't it? The bottom function never changed, right? And this entire time, our bottom function was always this guy. But there was a shift. And so what I can do is just find those two regions separately, can't I? Find the region first that had a top function of y equals x, which would be all of this function. But what is that y value, or that x value right there? I would be integrating from 0 to what? 1, right? It would be where those two lines intersected, right? Where y equals 1 and y equals x intersect, which means x equals 1. So I would integrate that first section from 0 to 1, top function being my y equals x. Bottom function is this curve right here, x squared over 4. And then we shift because now my top function changes. And so this region becomes a second integral. And it starts at 1 and goes to where those intersect. Remember, I can set my equations equal to each other. If I'm not sure where those intersect, solve for x. So I would integrate from 1 to 2, where they intersect, right? And my top function is 1, and my bottom function is x squared over 4. So you can break up one shaded region into multiples, especially if something like your top function or your bottom function changes in that original interval. I want to say this is some really small number. Who's got that typed in? All right. I just want you to go back and kind of think about what I was talking about here. As you travel across your shaded region, if your top function or if your bottom function ever changes, you're probably going to have to break it up into multiple intervals as you're doing that. And that can help you a little bit through some of the problems you are doing on your assignment tonight. With that being said, one of your assignments tonight does involve variable answers. You do not have an actual interval. That's number 19. So number 19 is going to be a little bit unique. And the other one I want to highlight on this one, the one you are turning in on a separate piece of paper tomorrow, is number 10. So show me all of your good work, your setup of your intervals, all of that. Number 1 is the only one that I would say you are allowed to use Math 9 on. Other than that, you should be doing your work analytically or via pencil paper to find your areas.